Hi, my name is Sheel Dodani, and I'm an associate professor of chemistry and biochemistry here at the University of Texas at Dallas. I started my research program in 2016, and today I'm going to share with you a little bit about the work that was published in Chemical Science recently. The authors on this study include Wei Chang, who is a PhD candidate in my lab. Caden and Hugh were fast-track master's students. Jacob was a former undergraduate. Jasmine is currently a postdoctoral fellow. Shelby is a PhD candidate, and Sam is a former graduate student in the Maloney lab. And finally, my colleague Gabriel is also on this manuscript. Anions are largely considered to kind of be the counter ions of life, but they really have many functions ascribed to them. And so what I wanted to bring to the table was an understanding of how we can study anions in a biological context. And this is what really spurred us in this direction. So I approached how we think about anions through a coordination chemistry perspective. How can we go into water and then a living cell and beat nature at its own game of interacting with an anion? And that's the big penalty that we have to pay. How do you desolvate an anion in water? And if you can't do it with a molecule as effectively, can you do it with a protein? And so when we started this project, we started thinking about the chemical approach and the biological approach. And I saw that there was more, so to speak, synthetic diversity in the biological approach than I could access with a traditional synthetic approach. And so those ideas are really rooted in the concept of supramolecular chemistry, where we think about the guest, that is an anion, and of course the protein, which is the host. But from the perspective of tunability and diversification, proteins afford what I believe is equal, if not greater, tunability than a synthetic system to achieve this goal. So this project really represents the springboard for us to move into cell biology. It is the first paper where we are starting to understand how we can put our technologies into a living cell to basically illuminate, unintended, how anions function in biological systems. So Gabriel has an expertise in understanding the kinetics of binding of metal proteins. And he has the right setup to do one of the experiments that we have in this manuscript. So he and his student Sam taught Caden how to actually do the experiment. And Caden was able to go into their lab and use the setup to start to understand how we can understand the kinetics of anion binding to fluorescent proteins. Now that we have kind of all the necessary parts set up in our lab, we can start to not only continue to engineer new protein systems, learn how nature is encoding anion binding, but also develop rigorous methods so that we can widely disseminate our tools. And I bring this up because this is really important as a tool maker. You want someone to use your tool to answer a question that they might be interested in that you don't necessarily want to answer, but you can enable it. And I bring this up because the sensor that we have reported in this paper is actually now available to researchers on the Agene website. So that's a really important piece to me, that now we can kind of move forward and start to share our technologies with a wide range of researchers, while also advancing some of the questions that we're interested in answering. The major reasons why we published in Chemical Science is our ability to reach a broad audience. As I mentioned to you, we're quite interdisciplinary in our approach, and our goal is to understand, one, how proteins bind anions in water, and two, can we engineer the protein to then give us a functional output to start to answer questions about anions in a biological system. And so the goal is that I can reach a wide range of readers who may have some overlapping interest with my research team's goals, but also in that we draw inspiration from many of the readers in chemical science. And that's the goal, is can we teach someone something new about our work, and can we learn something new from someone else's work? And I see that in chemical science whenever I pick up an issue.